In the last lesson, we discussed electromagnetic radiation, and we discussed it in terms of wavelength and frequency. So just as a quick reminder, remember that wavelength is the distance between two crests or two troughs. It's measured in meters. And the frequency is how many times a crest will pass a given point in 1 second, how frequently it will pass that given point. And its units are either seconds to the -1 or hertz. Now I'm going to add one more variable into the mix, and that is energy. Before I discuss energy and how it relates to wavelength and frequency, however, I need to discuss a term that you will hear quite often, and that's quantized. Okay? When we're discussing electrons and the energy that they have and that they'll release and that they absorb, we say that that energy is quantized. So quantized means that there are specific energy levels. And the best way to think about this is a bookshelf. So notice here I've got my nucleus, okay? And then I have specific energy levels. So I could have a first energy level that's represented by n equals 1, second energy level n equals 2, n equals 3, n equals 4, n equals 5. And you see that in this Bohr model here, right? You've got your nucleus, energy level 1, energy level 2, energy level 3, etc. The reason why I'm showing you a bookshelf, though, is for you to understand this concept of quantized. So just like for a bookshelf, I can only put books on a first shelf, a second, a third, a fourth, not on bookshelf number 1.5, because there isn't a platform for that book. So with electrons, they can only occupy very specific energy levels, 1, 2, 3, 4, 5, and those energy levels correspond with very specific amounts of energy. Okay, so that's what we mean when we say that electrons are quantized. They need to occupy a specific energy level, and that specific energy level will lead to them having specific energies. So what we're really going to be looking at in this lesson and then in the next lesson is actually fireworks and how fireworks work. So we've got to get into what's happening with subatomic particles in this lesson, talk about the math in this lesson, and then we get to actually see some fireworks for ourselves and really understand how we get the very distinctive colors that are observed. So if you notice here, I've got my atom. Okay? And so what happens in fireworks is, let's say, for example, I have an electron that is in the first energy level. Okay? What happens is energy is provided to that electron, which allows it to absorb energy, and it will jump to a higher energy level. So what happens to an electron when it absorbs energy? It jumps to a higher energy level. If that's all that was happening in fireworks, we wouldn't see anything. Okay, so our electron has jumped from the first energy level. Now our electron, let's say, for example, is in the third energy level. Okay, so it has gone from what we call the ground state here in the first energy level. That is where it is stable, where it naturally wants to exist. And by providing it with energy, it is now in what we call the excited state. And just like with kids, the excited state, or being super hyper, is not stable. So when this electron absorbs energy, it will jump to a higher energy level, and it will exist in this excited state, but not for very long. It will then want to go back down to its ground state to be more stable. And when that happens, it releases energy, and it will jump back down, or it will move back to its original principal energy level. So it will move back to the lower energy level. All right, so why do we care? Well, when that electron goes from the excited state back down to the ground state, in order to do that, it is releasing energy, and it releases energy that has a very specific energy of electromagnetic radiation. So this energy that's being released is electromagnetic radiation. Which begs the question, again, why do we care? Well, that electromagnetic radiation actually is within the visible spectrum. And so when that energy is released, we see it as those distinctive colors we see when we see fireworks. So those awesome turquoises, those electrons are in their natural ground state. We excite them by providing them with energy. Nothing happens. We don't observe anything. But that electron in its excited state is not stable, so it will go back down to its ground state. When it does that, it releases energy in the form of electromagnetic radiation, and that electromagnetic radiation is what we see when we see fireworks. So here are a couple of examples. Okay, so you've got strontium. If we did this to strontium, so what we'll do in our lab is you actually take a strontium compound and you put it into fire, and what you'll see is a gorgeous red color. And that gorgeous red color is the result of a number of different electrons jumping from their excited states back down to their ground states, right? Because by putting it in the fire, we excited it, and now it's going to jump back down. So if you notice, you've got a number of different lines here. Each of these lines, so there's 6 different lines for strontium, represents an electron making one specific jump. So from one energy level, different jumps that happen. When those are combined together, what we observe is that gorgeous red color, but it is actually 6 different very specific transitions. For barium, you see an awesome green color here, and that's a result of all of these different transitions. These are all different jumps that electrons make. I can't even go small enough to show all of them, but when they combine all together, they form this green color. Now, the way that we can actually see these individual lines, we can use a prism. And so what a prism does is it actually breaks up all of the different colors that are being released, all of that visible light, so that we can see the individual parts, okay, that make up that red or that green color. Another example of a prism that you experience, not in your everyday lives here in Los Angeles, but you've often experienced, is a rainbow, right? Because white light involves all of the different colors of the visible spectrum. And the only way you get a rainbow is if you have water. And so water is acting as the prism in order to break up all of those different colors of the visible spectrum. Okay, so that's the concept we're going to look at further with fireworks. Let's actually look at our formula. Formula for energy is that energy equals Planck's constant times our frequency. Okay, so let's go through units. Your units for energy are going to be in joules. So I'm going to spell it out for you, but then we write for our unit, we just write a capital J. H is Planck's constant and is a value that you will always be given, and it never changes. And that value is 6.626 times 10 to the negative 34th. And my units are going to be joules times seconds. Okay? And remember your nu, that is your frequency. And the units for frequency are going to be either seconds to the negative 1 or hertz. Okay, so notice with my Planck's constant, the units for Planck's constant are joules times seconds. If I'm then multiplying by seconds to the negative 1, joules times seconds to the negative 1, or 1 over seconds. Notice my seconds cancel, which leaves me with my unit for energy, which is joules. Okay. All right, well, how are wavelength, frequency, and energy related? Well, we already know that wavelength and frequency are inversely related.
So that begs the question, how are energy and frequency related? Well, if you think about it, if you move a slinky very slowly up and down, it'll create a wave that has a very long wavelength and a low frequency because you're applying very little energy. If you increase the energy by shaking the slinky with more and more and more force, the wavelength, the distance between the crests, is going to decrease while the frequency increases. And so what that tells us is that energy, the energy that you're putting into the slinky, and the frequency are directly related.
So energy and frequency, when one goes up, the other goes up as well. We call that a direct relationship. They are directly related. Okay? Which begs the question, if energy and frequency are directly related, that means energy and wavelength, what is their relationship? Well, their relationship is going to be inversely related, since frequency and wavelength are inversely related. Okay, so let's do some actual math practice problems to see how to calculate energy. All right, for number 1, it says tiny water drops in the air disperse the white light of the sun into a rainbow, as we just discussed. What is the energy of a photon from 23 times 10 to the 14th seconds to the negative 1? All right, so I've got my formula. Energy equals Planck's constant times my frequency, my mu. Okay. I'm solving for energy. I know my Planck's constant. I'm going to multiply that by my frequency. And the unrounded value that I get is 4.7905, and I'm going to stop after the 9, times 10 to the negative 19. Okay, I'm going to quickly round. So 6.626 has 1, 2, 3, 4 significant figures. 7.23 has 1, 2, 3. So I want my final answer to have 1, 2, 3 sig figs. So when I round this, I get 4.79 times 10 to the negative 19, and my units are joules. So I checked for sig figs. I checked for my units, and I'm good to go. Let's try the next one. X-rays have an energy of 2.0 times 10 to the negative 15th joules. What is the frequency? So now, using my formula, I'm given the energy, and I'm asked to solve for frequency. So I'm going to plug in this for my energy, 2.0 times 10 to the negative 15. Okay. I know my Planck's constant, and I'm solving for frequency. Okay. So what I'm going to do now to solve for frequency, I need to divide both sides by Planck's constant. Keep in mind when you're plugging this into your calculator to put Planck's constant in parentheses, or else your calculator will divide by 6.626, and then it will multiply by 10 to the negative 34th, which you don't want it to do. Okay. I'm going to divide by my Planck's constant, and the unrounded value that I get for my frequency is 3.018 times 10 to the 18th. Keep in mind, 2.0 has 2 sig figs. 6.626 has 1, 2, 3, 4 sig figs. So I want a total of 2 sig figs, 1, 2. So this is going to round to 3.0 times 10 to the 18th. And keep in mind my units for frequency are going to be seconds to the negative 1 or hertz. Okay, let's look at the next problem. All right, microwaves have a frequency of 3.0 times 10 to the 8th kilohertz. What is the energy of this electromagnetic radiation in joules? Well, here's my problem. This is my frequency, so I would love to plug it into my formula for energy equals Planck's constant times mu. However, keep in mind your frequency has to be in hertz. So what I'm going to need to do is first take 3.0 times 10 to the 8th kilohertz, and I need to convert that into just regular hertz. So I know how to do that. That's not too bad. I'm going to get out of kilohertz by putting it on bottom. and I'm going to get into hertz. Okay, so I know for every 1 kilohertz, there are 10 to the third hertz, which means my hertz here, I'm going to have 3.0 times 10. Keep in mind when I'm multiplying by powers of 10, I add their exponents, so 8 plus 3 is going to give me 11. 3.0 times 10 to the 11 hertz. Now I can plug this frequency value in to determine my energy. So energy is going to be Planck's constant times my frequency, which is 3.0 times 10 to the 11. And so the energy I get here, unrounded, 1.9878 times 10 to the negative 22nd. Let's figure out Sig Figs. 6.626 gives me 4 Sig Figs. 3.0 is 2 Sig Figs. Okay, so this is going to round. 8 rounds the 9 up, which is going to give me 2.0 times 10 to the negative 22nd. And keep in mind, because I'm solving for energy, my units are going to be joules, which is what the problem asks for. So I have already checked Sig Figs. I've checked units. I'm good to go. All right, for the next one, a wave has a wavelength of 2.44 times 10 to the negative 7th meters. Calculate the energy. Energy equals Planck's constant times my frequency. Wavelength is not in there, which creates a problem. So what I'm going to have to do is I'm going to first have to figure out what the frequency is by using the formula we used in the last lesson, which is the speed of light equals my wavelength times my frequency. Okay? So let's plug in the values I know to solve first for frequency, and then I can plug it in to figure out my energy. So my speed of light is 3.00 times 10 to the 8th. Okay? My wavelength is 2.44 times 10 to the negative 7. Okay? And I'm solving for my frequency. So to solve for frequency, remember you've got to divide both sides by 2.44 times 10 to the negative 7. Do keep in mind when you are dividing with your calculator in a second to put the 2.44 into parentheses in your calculator. Put that in parentheses just to remind you. Okay? And when I get unrounded, and I'm going to keep it unrounded, is 1 point, within reason obviously, 295, and I'm going to leave it there because the next digit is 0 times 10 to the 15th. Okay, so no, I'm not going to write out the entire value, but I'm not going to round this yet because I'm not done. I now need to take my frequency and I need to plug it in to my energy formula. Okay, so here I know energy equals Planck's constant times my frequency. Now, what I would recommend doing, I had just calculated my frequency. Leave that in your calculator, so you have your 1.2295, and it keeps going. Now, just multiply by 6.626 times 10 to the negative 34, because that way, you don't have to retype in your value, and you won't be rounding, because even though I wrote 1.2295, that is slightly rounded. Okay, so just keep it all in your calculator. And so what I get for my energy, unrounded, is 8.146, let's say 7, times 10 to the negative 19. And my units are going to be joules, because I'm dealing with energy. Let's figure out Sig Figs. We need to go back to the original problem. So values that you used, I used 2.44, which has 3 Sig Figs. I used 3.0, which has 3 Sig Figs. And I use 6.626, which has 4 Sig Figs. Okay, so those are the 3 values I need to be looking at. So I need to have 3 Sig Figs in my final answer. 1, 2, 3. Here is going to be 8.15 times 10 to the negative 19. And my units are going to be joules.